In this video, I'm going to explain linear independence, linear dependence, and linear combinations. I'm going to start out with some geometry to describe what linear dependence is. So I'm going to draw two vectors. And now we could say that the pink vector is the vector 1, 1, and the brown vector is vector 2, 2. But really, this brown vector is just 2 times vector 1, 1. So really these directions are the same. They're just different in their magnitude or scale. So they're really the same vector, just one is multiplied by a scalar. And so that's an example of linear dependence, when the vectors are in the same direction, but just differ in their scale. Another example is if we have 3 vectors this time. And so I'm not going to assign numbers to this, but let's say we move this blue vector like so. So now it looks like the blue vector plus the red vector equals the green vector. And so this is a linear combination of vectors. And when we have a set of vectors, and we can describe one vector in the set using other vectors in the set, those vectors are in a linearly dependent set. Now I'll assign numbers to the vectors. We'll say the blue vector is -1, 1, the red vector is 2, 1, and the green vector is 1, 2. And now we'll turn this into a matrix. We just combine all the vectors together, and we get this. And then once we row reduce this, we'll get the matrix 1, 0, 1, and 0, 1, 1. And what you'll notice is that there's 2 pivot positions in the first and second columns, but there's no pivot position in the third one, which means we have a free variable in the third column. And that's true for all linearly dependent vectors. If you have a set of linearly dependent vectors, then there will be a free variable in your matrix. So if it's linearly independent, the matrix will not have a free variable. And this makes sense because if it's linearly independent, you can't take one vector in the matrix and form it using other vectors in it. But in this linearly dependent matrix, we can describe the first 2 columns, the first 2 vectors, in terms of the third vector. Say we want to find ax equals 0 for this matrix. And so then x1 will equal -x3, and x2 will also be -x3. Because we're able to describe x1 and x2 in terms of a free variable, then we have a solution to ax equals 0 in which x does not equal 0. And so our matrix is linearly dependent. So I'm going to say that again because it's important. An aspect of a linearly dependent matrix is that there is a solution to ax equals 0 in which x is not just the 0 vector. Now I'm going to show you a way to immediately identify a linearly dependent matrix just by looking at it. And so what we determined before is that this matrix is linearly dependent. And we're going to call this matrix A. And matrix A is an m by n matrix. We know m is the number of rows, so it's 2, and n is the number of columns or vectors, so it's 3. So we have a 2 by 3 matrix. And so what we showed before is that this variable was free. And that's going to be true for every 2 by 3 matrix. Because we can only have 2 pivot positions because we only have 2 rows. So that limits the amount of pivot positions we have. So that third column is always going to be free. And so what this means for an m by n matrix, for an m by n matrix, if the number of rows m is less than the number of columns, then the matrix A will always be linearly dependent. And that's true not only for 2 by 3 matrices, but it could be a 1 by 2, a 2 by 4, 3 by 4. Anywhere the amount of rows is less than the amount of columns, the matrix will always be linearly dependent. Going back to graphs, here's an interesting way of thinking about linear independence and dependence. So this is the xy plane, which means we're in 2 dimensions. And we can denote this as R2. We're in R2. So that means every vector we have will have 2 components. an x and a y component. And so we can think about this as if we have a certain number of vectors, is it possible to write another vector that is perpendicular to all the vectors in the plane and still be linearly independent? And so if we have one vector, this is true. We can create another vector that is perpendicular. But if we want to do that again, well, we can't write it here because this is the same direction as the purple vector. And we can't write it here. This is the same as the pink vector. It's just a negative scalar. And so because we can't write another vector that is perpendicular to the two given vectors already, then adding any vector to the two given vectors that we already have will force all three of them to be linearly dependent. And so let's say we draw one that is neither perpendicular nor in the same line or scale as the other two. So we draw a vector right here. Well, then this is going to be x1, y1, x2, y2, and x3, y3. And so we'll have 2 rows and 3 columns if we turn this into a matrix, and we already determined that that makes it linearly dependent. But we can also think about the span of the vectors. So this blue vector falls within the span of the pink and purple vector, or the pink vector falls in the span of the purple and blue, or the purple falls in the span of the pink and blue. And because one of the vectors falls in the span of the other two, it can be described in terms of the other two, and thus the vectors are linearly dependent. We can also think of this in terms of 3 dimensions, or even more dimensions, but this is x, y, z, which is 3 dimensions, and so we denote it R3. And so vectors in R3 will be described in terms of x, y, and z. So we start with one vector. And can we write another that is perpendicular to this one and also linearly independent? Of course. If we're able to do it in 2 dimensions, we can do it in 3 dimensions. Now because we're in 3 dimensions, we can even write another one. If we say that the purple one is along the x-axis and the blue one is along the y-axis, we can draw this a little better to represent that. And then we could say the pink one is along the z-axis. And so all those vectors are both perpendicular to each other and linearly independent of one another. And again, notice that we're in R3 and have a maximum of 3 linearly independent vectors. But any more, and we'd either be writing it in terms of the blue vector, purple vector, or the pink vector. Like and subscribe for more.